All right, thank you. So we are Project 9, if you were still awake. So there's us and one more to go. You're doing great. So we were numerical simulations using Ramsey's and Arabo codes. These are both of the codes that Simon presented in his lecture. So you might have to think back a little bit. So this is NGC 628. This is probably a JWST image that you've seen many times by now. If not, now you have. This image is really exciting because it's really introduced extra research into shocks, because as you can see, there's a lot of bubbles in this image, and we added one more. But these are really important, as we've discussed in the lectures, to the ISM. So hopefully I don't have to convince you on that. So what we actually did for our project is, after understanding that this is something we wanted to work on, we split into two different methods. Part of our group worked on developing actual simulations using Ramsey's of different shocks driven by supernovae. And the rest of our group worked on data processing using already run simulations from a repo. We used one snapshot.
Thanks. I want to give you a bit of a background of what to expect when you look at our simulations. What we try to simulate and look at is mostly supernovae shocks. And for our purposes, this is mainly an enormous injection of pressure at one point in our space. And what happens is that all the material will be pushed outwards at enormous speeds, initially so fast that the motion is ballistic and not well described by hydrodynamics, and very fast. And then after a short while, when hydrodynamics is a good description again, you will end up with an inner region where everything is very supersonic and an outer region where it's still subsonic. And you can look for solutions to the hydrodynamical equations. You will find that you will have solutions that are always subsonic. You will have solutions that are always supersonic. But you will have no solutions that can be both supersonic everywhere outside and inside, and subsonic outside. So what you will end up with is a shock, a discontinuity. You will find no continuous solutions. And you can find out some of the properties of this shock by a very simple estimation. If you look at the continuity equation here in the shock rest frame, so where the shock is at rest, so all your time derivatives vanish. So the continuity equation reduces to this very simple form of the conservation of mass. And if you have a post medium, an outside medium that is much more dense than what is inside, so everything has expanded already, then you can reorder this equation and you will find that the post velocity after the shock has passed through is much smaller than the pre-shock velocity. And now note, this is in relation to the shock rest frame. So what has been shocked moves along with the shock, is what this is saying, in other words. So if I put this into maybe more understandable sentences, the flow is compressed and slowed down in the shock rest frame. And what the shock does, it is converts bulk kinetic energy into heat.
So to model those supernova bubbles, we relied on the Ramses code, as we said before. So here are some technicalities about the Ramses code, but what you have to keep in mind is that it uses a Eulerian approach, and it's really great using the adaptive mesh refinement, as we can see here. So it's really great for multi-scale resolution and which are involved everywhere. And so if you have a question to discuss with Man and see his lecture. So we used the Ramses to first on really simple 1D and 3D models, not a really straightforward simulation to do, but we used that, and then we created our own input file in order to create our own set of instability. Yeah.
Okay, so we had some nice movies, but sadly this is a PDF. First of all, we have a simulation of a very normal supernova with 1 times 10 to the 51 ergs. The surrounding medium is 100 helium, or like a hydrogen per cubic centimeter, and the initial pressure inside. So the initial setup is we have an over-pressurized region of 0.55 parsecs with a high pressure of the supernova, and then it expands. And as you can see here, like the top, so top left is pressure, bottom left is density, and top right is the pressure profile on one axis, and down right is the density profile. And as you can see, the density has a spike there, it's a shell, and same in the pressure, where you have like this continuity. Then if we plot wait. Okay, so if you take the measure from here to here, how big is it? That is like the shell radius. And if we plot the shell radius over time, then we get this, where the blue line is the theoretical. Does it work? No. Yes, now it works. And the red lines is the end of the set of Taylor phase, which is like the thing we are kind of simulating. And as you can see, there's a quite good approximation. And yeah, so that kind of works. Then we have the same thing with the energy of 100 supernovas. And here on the right-hand side, you can see the result. Yeah, and they are pretty much similar, not much going on. However, we have a third simulation. This has a magnetic field.
Okay, I'm sorry.
So yeah, this simulation has a magnetic field of arbitrary strength because I couldn't figure out the units. And as you can see, this actually kind of differs in the profile and also like in the shape of the whole supernova. And so basically what's going on, like it easier expands along the field lines and it's getting suppressed perpendicular to the field lines. And we can also see that in this plot. So where like the red, like the green points are like along one axis and the yellow points are along the other axis. As you can see, it's no longer spherical and instead it's getting ellipsoid. Yeah, okay.
Okay, I'm going to run through this second part really quick. But the second part of our project is we built our own bubble finding algorithm for this Arepo snapshot. So we need to be a chef and slice our galaxy snapshot into cubes, and then we can search each cubes for a minimum density. We know the inside of a bubble is a hot, very low density volume filling component. So we're going to select that least density, find the coordinates of these particles, and this is the center of our bubble finder. So then once we actually have a bubble, this was our best example. So of course we're showing it to you. We compute all of the properties in different shells to see how that changes with radius. This is the actual size compared to the galaxy. So it looks large, but remember how small this is on the grand scheme of things. So we can see density and thermal pressure increase with radius, as we would expect for one of these bubbles. And radial velocity increases until we get to shells that are outside of that dense shell.
To finish it off, we'll look at what went wrong. So we first use the radial velocity to determine what is the size of a bubble and establish the radius, and then run this algorithm over the entire volume, and we find like 15-ish potential bubbles. Some of them are kind of like bubbles, but we could not verify them all. But most of them are not bubbles. So this is because outside the volume, we are not very sure of the spherical geometry, because as the bubble expands, and we saw in the previous lecture this morning, they don't really stay spherical. And also, these supernovae are not really isolated like we did in the Ramses simulations. Yeah, things can go wrong. And this is one of the big failures that we had, where we classify this as a bubble, but it's not really a bubble. So I guess that is it. Any questions? We're happy to address them. Thank you.
I think that's exactly.
Nice speedrun.
Is the size of the Arepo simulation big or is it small? Does it fit in a computer? No, no. Does it fit in the computer? In a
Yes. each snapshot is around like 2.5 to 3 gigabytes. So we could barely run them on our computers.
Mhm.
So that is why we were not able to do like a very refined integral. That's why we also have like a resolution limit to what size of bubbles we can find, because our shells were 75 parsecs, which is fairly large.
Do you see bubbles? Do you see shocks in all the bubbles?
We did not really do like a line profile to find the discontinuity, because if we go back to this method, we are basically integrating over the shells to find out the density, and that shell is 75 parsecs. And if you were to do that at the shock front, you would smoothen it out. So you would basically see something that goes like this, not really that. Yeah, it's just we'll need finer shells. And also we didn't have enough particles within this region to be able to resolve this structure because it's quite small.
Can you identify shocks with velocity field?
Can
Then?
you repeat?
Can you identify shocks with velocities then?
With velocities, partly yes, because we expect, because this is an outflowing gas, which is very hot inside, we expect the radial velocity to be positive inside the bubble. And as soon as we get out, the ISM is doing its own thing. It doesn't really know about this bubble. So the radial velocity should like immediately die off after we go out, like once the shell is outside the sphere. Yeah. So that was the reliable measure that we used, but we could in principle use the density or the temperature profiles or something else. We did not try those.
Okay, I see. Thank you.
Oh, wait, we did try density. It did work well. We did try density. Okay.
Okay, thank you.